linear. And I'm also going to discuss where they appear, especially since this is a mathematics department, and our topic is a general discussion on algebra. I'm going to discuss how matrix theory fits to all of this. So I'm going to give you a plethora of examples. Of course, I don't know all of your background here, so of course I assume you're not engineers, you're mathematicians, just like myself. So I'm not really going to go into details in every example we're going to give, but I just want to give you a whole impression of where descriptor systems may appear, because, going from your bachelor degree to probably master's degree or PhD, some of you may go towards biology, some of you may go towards engineering, mechanical engineering, chemistry, and I want you to be aware that no matter where your specialization is going to be in the future, potentially you're going to meet descriptor systems in your studies, and that's what I want you to keep from this discussion. So there aren't going to be a lot of mathematics here, just a whole presentation of descriptor systems. So yes, I'm going to discuss mechanical, electrical, economic systems, biological, cyber physical, some nonlinear examples, and I am going to discuss a bit more about the application of secure communications that I do on my postdoctoral work, for which I'm also funded here by the State Scholarship Foundation. And then we're going to discuss the linear algebra tools. So let's begin. Okay, classic state space systems. Of course, a lot of our previous discussions and lectures today and yesterday were about state space systems. So the state space systems, they have a very simple formulation, especially linear ones. Professor Vikas also talked about that previously. They are very classic systems. They are supposedly unconstrained in continuous time or in discrete time, as you see here. And, they have a very clear distinction between what is the input of the system, which is U, the internal states, which is X, and potentially we also have some output, which is Y. So we have a very clear distinction here between input, state, and output. And these systems, they are very simple in form. As you can see, they are, nothing else than a set of linear differential equations. And they describe a plethora of phenomena. They are very well known in the engineering practice. Practically, they have been around for 60+ years, and they have been popularized by Rudolf Kalman. You may have heard the term Kalman filter. It's this guy who actually did it. And, he was one of the main researchers in the Apollo project. So, when people sent, USA sent people to the moon, one of the main researchers for the project was Rudolf Kalman. And he was the one to popularize state space systems, which are nothing more than simple sets of differential equations. And they can be extensively studied, through linear algebra. So these are classic state space systems. They have been around for a lot of years. So what are descriptor systems? Descriptor systems are actually an extension of state space systems. And what is differentiated here from before is that we have differential equations or difference equations in discrete time, but also we have some algebraic equations. And why does that happen? This happens when we have systems that appear, to have also some sort of constraint. So, descriptor systems generally appear on systems that have constraints. They can naturally arise when we have some sort of physical or artificial systems where the variables describe quantities like volume, voltage, displacement, which all have a natural meaning, and can usually be some sort of subject to a restriction. So descriptor systems model exactly that, the possible restriction on the physical quantities of the system. And the general form is this. As you can see, it's sort of similar to state space systems, but the difference is this. The derivative here, x dot, is multiplied from the left by a matrix epsilon. And the matrix epsilon here, in general, we assume that is non-invertible. Okay, so it's singular. Because clearly, guys, if the matrix was in this case, the matrix is non-invertible. And these sort of systems, they are called singular systems or differential algebraic systems or simply DAEs. And, so let's say, okay, the system has some form of constraints, so it's a more general form than state space systems. So my question is this, okay, since we have physical constraints, how does this system, that was initial state space, but now it's descriptor, how is it different? Do we have any issues? What sort of problems do arise here? And the answer is that we have a lot of different problems arising in contrast to state space systems that, make the analysis and the design and the control more difficult. And for example, in continuous time, we may have impulsive behavior. That's the behavior where, at time zero, we have a sort of very, very strong but instantaneous pulse in the system that can potentially destroy the system. We have the problem of non-uniqueness of solution. So, we can have different initial conditions, but they give rise to the same solution. So we have, non-uniqueness. In discrete time, we may have non-causality. So the system, we may have a formulation that depends on past states, but also on future states, which doesn't make much sense, but it can also appear. And potentially, we can even have non-existence of solutions. So, there may be a case, oops, I'm terribly sorry. There may be a case where, the solution may not at all exist. And, this makes the whole problem of studying controllability, reachability, observability, pole placement, more difficult overall. So, where do they arise? I mean, okay, from a mathematical standpoint, they sound very interesting. But where exactly do we have descriptor systems? They appear in continuous time. They can also appear in discrete time. And let me remind you that sometimes in computer-aided design, we take a continuous system and we discretize it. So, for example, in discrete time, we may have a discrete population model, or we may have a continuous model, mechanical, that is discretized to be used in the computer. So, discrete time systems can appear in many different examples. So let's begin here with some examples of mechanical systems. You can hear me, right?
Yes, we can hear you.
Cool. I'm anxious in case we have some difficulties in communication. Okay, but okay, since you can hear me, let me continue. So let's begin with mechanical systems. Mechanical systems, they have this sort of very general form. This is a classic, model, for example, describing mass, for example, two masses connected with a spring and a damper. So we have an external force, and we have the damping and stiffness coefficients and the mass matrix. In general, these are state space systems, but in some cases, this system may transform into a descriptor form. Where can this appear? Well, for example, there are some research directions and some research groups that they have shown that in case you have multiple bodies in the system, in order to derive the equations of motion, it may eventually be easier to derive them if you use more than the minimum number of coordinates. I will explain that in the next slide. So, in some cases, it may be easier to derive the equations if you initially try to model the system independently, instead of trying, to create a combined coordinate system that includes all the masses. And in this case, the matrix here M may be non-invertible. So we have a descriptor system. And the second case where descriptor systems may arise is when we have massless bodies. So when we have bodies that don't have any mass. So let me explain without many details these two examples. For example, here, this is a classic spring mass system. Okay, we have a system with two masses, two springs. Potentially, we can have dampers as well. So, initially, you want to try to model the system as it is. You have the first displacement and the second displacement. So, this research group has actually showed that in order to derive the equations of motion, it may actually be easier to take this mass as a separate system, this mass as a separate system. So now you have three actual displacements, x1, q1, which is actually x1 plus d here, and q2. And that's what I mean. You have more than the minimum number of coordinates. You use more coordinates, and the idea is this: model this system independently as a single system. Model this system independently as a single system. Of course, you may have a third, a fourth, a fifth mass. So model each system independently, and then see how these coordinates are, connected to each other. For example, here you have that the Q2 is actually Q1. I'm sorry, let me rephrase this. You may have the constraint here, which means that Q1 is actually X1 plus that. So, you have a algebraic constraint. So the idea is this: you model them independently, and then after some procedure, you may end up you need to incorporate the constraints of the system, and eventually you may end up with a state space system. But the idea is this: you model them individually to have them to easier, in a more easier way, define and decide what are the equations of motion. And if you go and model them, this system this way with independent submodels, you may end up with singular mass matrices, which they appear right here. And by the way, this design you can model, for example, a building where each mass is a separate floor. You can model a spring mass damper system in your car. So there are many different applications for this type of spring mass systems. So this is one example where singular matrices may arise. Another example is the one I told you about massless bodies. So let's say here, for example, you have a mass, and you have two different springs with different coefficients and two dampers with different coefficients, and they are connected to each other. So in that sort of example, you may have to assume that these two springs are connected right here, and the dampers right here, but there is no mass here. So you may artificially assume that there is one mass right here and another mass right here, so another body, but their mass is actually 0 kilograms. So in this case, where the masses here are, the bodies here, let me correct this, they are massless, you may again end up with a mass matrix that is non-invertible. So again, the system here may take a descriptor form. So as you can see, massless bodies also lead to mechanical systems like that are descriptor. Another very large example that we will meet, again and again in our next presentation is this example of interconnected systems. So, for example, let's say you have a lot of state space systems, individual ones, but they are interconnected to each other. So, similarly to the previous design, we may have a set of state space systems, and additionally, we may have some sort of algebraic equations that connect these subsystems to each other. For example, let's say you may have the input to one system become the output to the other system. The state of one system may be the output or the input to another system. So you need some sort of constraints, algebraic relations, to show us how these systems relate to each other. So again, you may end up with algebraic constraints. For example, the input to the whole system may be the water flow. So if the water flow then goes through different pipes, of course, the sum of all those pipes needs to be equal to the initial water flow that you provide to the system. So again, naturally, it is very natural to assume that this sort of algebraic constraints will appear. An example is this, for example, we have a tank level control. So assume here that Q1 plus and Q2 and Q3 is the displacement of the water level. So let's say that, for example, if I increase the pressure right here, the water level is going to go up, and understandably, the water level in here and here is going to go lower. Of course, this sort of imbalance between volumes needs to be corrected, right? It always needs to be equal to 0. So in this case, the algebraic constraint is this, for example, if I have some sort of higher volume in one tank, then obviously we need to have lower volume in the rest of the tanks, because the water in all three volumes remains always the same. So here, the constraint relation will be a result of the mass balance between the three volumes. Again, very naturally, we see that the descriptor system arises in order to model the fact that the mass in all three volumes, in all three bodies, remains the same. So again, a very natural arise of a descriptor system. This is a sort of volume balance descriptor case. Another case is a three-link manipulator. So this is again a very complex system, but you know, in the papers that I cite, they're actually very simplified. And the constraint here may appear from the fact that this sort of last beam needs to always be adjacent to the building, so it always needs to be close to the building, and it also needs to be vertical to the building. So in this case, for example, we may have a sort of geometric constraint. This is signified right here, when we need, you know, the third beam to actually be always in contact and orthogonal to the cleaning surface. This is sort of a geometric constraint, if you like. So let's move on to electrical circuits. Again, this is a subject that I'm not really very familiar with, but it's very easy to understand that this is a great example of where impulses may arise and where we also may have constraints. For example, think of that. Think of a circuit that at time equals 0, you may have some sort of switching between one circuit to another. So in this case, for example, where we may have residual voltage between one circuit to another, residual heat or something, at time equals 0, you may have an impulse because you know, we may have an inconsistency between the original circuit and the switched circuit. So, you know, in this case, impulses may arise, the system may be destroyed, you know, so ideally we don't want to have impulses. So this is a great example of circuits that may potentially be descriptor and have impulses. And again, in this sort of circuits, I have a lot of examples here. This is a simple RLC circuit. And again, you may be unfamiliar with this sort of design if you don't have them in your, you know, undergraduate studies. But let's simply say that, again, singular matrices may arise right here, which are non-invertible, due to the fact that we incorporate some Kirchhoff laws, for example, some fundamental laws like here, where, for example, we have that the voltage of the source is equal to the voltage in the resistance, inductance, and capacitance. Okay, so this sum here is actually Kirchhoff's law. If we incorporate it to the system, again, we may have some sort of algebraic constraint in the equations. And again, similar case with this circuit and with this circuit. Okay, and again, this is a comment by Verghese, which is a very popular paper. He actually comments on that, you know, because when switching appears, you know, you need to realize that you have a sort of a difference in the voltage in x0, in you know, a state at time 0 minus and the state at time 0 plus. So if you have a difference right there, the system very quickly or abruptly changes its voltage. So this may end up in a pulse generation, and this pulse in a mechanical system, in a circuit system, potentially can destroy it, you know, because we have, you know, a physical representation, potentially the system could be destroyed. So again, in descriptor systems, this is something that we generally want to avoid. Again, this is an example of where a pulse may arise. Now, something I really like, we move on to economic systems. Since, you know, you're from a mathematics department, so I'm pretty sure that many of you are going to go towards not biological systems or electrical systems or mechanical systems, that potentially may go and study economical systems. You know, mathematics are closely related to that. And again, in economical systems, we may have descriptor systems appearing. And this is a very simple example that I'm going to give. It's called the Leontief system. This is a discrete time system. So let's say we study, for example, the behavior from month to month in an economic model, or from 1 year to another year. And, you know, in this sort of economic models, we have a multi-sector economy. So, you know, each state of the system can represent a different sector of the economy. So as you can understand, these sectors, they are not, how should I say, they are not decoupled. They interconnect with each other, they interact with each other. So, you know, we may end up having some sort of, let's change the slide right here. We may sort of end up with a system that connects each state, each sector with another. We also have some sort of capital coefficients matrix that can give you the idea of, you know, to go from one period to the next, what sort of interaction do you need, what sort of money or deposit you need to move from one sector to another sector, and what sort of balance you need to have. Because, you know, if I have a steady income this year, I need to distribute it equally, or unequally among the different sectors. But again, in this case, we may end up with some sort of algebraic constraint in the system that may signify that, okay, these 2, 3, 4, 5 interrelating sectors of the economy need to have some sort of income balance. So again, theoretically, we may end up with a descriptor system where the matrix here is not invertible. Okay, so economic systems as well potentially could be described as descriptor systems. Biological systems, again, a very trending topic of discussion, especially since we are talking about the COVID era right here. So a lot of people, mathematicians especially, go into studying biological systems. And in many situations, biological systems can arise in descriptor form. For example, in this Leslie population model, here we have a sort of a state for the system that signifies the population divided into sort of age groups. So, let's say the first age group is 0 to 1 years, the second age group is 1 to 2 years, 2 to 4, and goes on and goes on. So in this case, we may have some sort of relation showing us that, okay, for the next year, people who are 0 years old are going to be some sort of linear, how should I say that? A linear combination of the births from all the research, from all the age groups. So, let's say that each age group gives a birth. So all these births are going to be part of the first generation group. So you may end up with this sort of matrix that, the first line is a linear combination of the births, and each individual line is actually the, how should I say that, the survival rate. So, if from this generation, some percent survives to the next generation, this is going to be the next state of the system. Of course, here if we assume that, for example, the last state of the system, which is like people that are 90 years old, of course, people who are 90 years old are not going to give birth. So this parameter here, which is the birth rate, may be equal to 0. So we may have a 0 column, which again, the matrix here may be non-invertible. And in case we're going to have some backward projection of this population, so let's say we have some measurements of this generation and the next generation, and potentially we want to assume what is the previous generation here, and the generation before, and the generation 3 years ago. So in case we're going to have some backward projection population, again, we may end up with a, a descriptor system model. So again, in population models, descriptor systems may appear. Sorry, going out, I see that, okay, we are still on the line, so let's continue. So population, polychamber models. Okay, remember I said talking to you about before in interconnected systems, in mechanical systems, that we have some sort of multiple state space systems interconnecting with each other. This sort of example is pretty much the same and appears again and again in different disciplines. For example, here we have a polychamber model. And by that, what do we mean? When we say chamber, we mean usually organs in the body. But think about it. Each different organ may be, simulated through, or modeled, through a state space system. So again, we have that sort of mechanical example where we had multiple state space systems, and then we had some sort of algebraic equation relating the balance or the mass between the income, the volume, the intake of its subsystem. So, the multiple economy model, here the polychamber model, which we actually mean the multi-organ model, they pretty much all of them fall into the category of mechanical, if you like, multi-body systems. For example, here we may have the distribution of some medicine to, for example, the kidneys, the kidneys, the liver. So these can be the different, models or the different sub-models of the system. And the algebraic equation, again, may represent the balance between intake and overall absorption. So, you give the patient the medicine, it's going to go through different chambers in the body, like the liver, the intestine, the heart maybe. And we have some sort of algebraic equation describing the balance between the distribution or the concentration of the medicine. So again, potentially you can have a descriptor system appearing in a biological system. This is another example which falls into the category of I'm sorry, of population dynamics. So, population dynamics, again, they are part of biology. For example, here, this is an example we found along with Vikas, who was presenting previously, which is an actually distribution model for diabetes. So the states here, for example, may be the people who have diabetes, the people who don't have diabetes, the people who die, the people who have diabetes, but on the next year they don't have anymore. And in describing the interconnection between all of these diabetes sections, we may potentially end up with some sort of descriptor system as well, because again we may have some sort of, how should I say it, net distribution or net migrations between one generation to another generation, or to healthy population to non-healthy, and non-healthy population to healthy population. And this sort of overall balance between populations again may give us a descriptor system. And actually, in this case, the system, we see that it is also rectangular. So okay, we have actually only one equation describing the whole model, but we have many different states. So again, for example, in this case, we may also end up with a non-square system. Next example, cyber-physical systems. Okay, of course, this is a case I'm very unfamiliar with. Now, cyber-physical systems, if you haven't heard of them, they are a very hot topic of discussion, especially among programmers and among engineers. They refer generally to transportation networks, power generation, distribution networks, water and gas distribution networks, or communication networks. For example, like a smart building, for example, I think it can be considered as a cyber-physical system, because it has a cyber part, which is actually the design and the algorithms running the building, and the physical part, which may be the air conditioning system, the water system, that are physical, but they are controlled from an artificial, from a digital controller. And in many cases like that, they use descriptor systems to model cyber-physical systems, again, due to the fact that they may have natural constraints, and they, of course, they are highly nonlinear. But I have seen papers where, in order to study some sort of simplified design, they consider a simply linearized form of a descriptor system. And again, they can also model disturbances, and they can model attacks, like cyber attacks on the system. So, they're very trendy topic of discussion. And again, they use descriptor systems to model them. For example, here I have a small example of a structure preserving power network, but I'm not going to discuss this in detail because it deviates a little bit from my research, and this is a highly hardcore engineering design. But you will see, and I can give you the citation for that they actually use a singular system. You see, it's a descriptor matrix here that they use to model the whole system. So again, descriptor systems can appear here as well. Now, as you saw, all of these systems that I gave you so far, all of them are linear. Okay, so, okay, still online. Now, if we move on from the linear case to non-linear examples, guys, believe me, there is an explosion of different designs and different examples here. So if you move on to the non-linear case, I mean, there is a plethora. There's like a billion different potential examples of this differential algebraic equations. So I'm going to give you some very, very simple examples here. For example, okay, previously I gave you some examples of biological models. Sorry, let's move on again. All right. But apart from the biological models like the Leontief economic model or the diabetes model, you can have economic biological models. You may not have heard this term, economic biological. When we say this term, actually we mean population models that have to do with harvesting. Okay, so let's say we have some fish population, for example, and we want to harvest it, and we want to see how much is it cost effective, how much money is going to give us. We want the population to survive, and in this case, we usually have some sort of dynamic equation describing the population dynamics. And we also have the algebraic equation here that actually describes the relation between economic interest and harvest effort. So this is going to give us a relation between how much effort, and by effort we mean time or money, how much effort we are going to give and how much money or income, or population growth we are going to get. And these sort of systems, again, you see they are non-linear, but again, we have an algebraic equation. So again, an example of a non-linear descriptor system. Of course, we may have even more complex designs compared to the previous one. For example, here we have a predator-prey differential system, which again, we have the prey that we may want to feed. So the prey is like, for example, some sort of krill or some sort of, food that we give to the predator. And then we have the population of immature predators. We cannot harvest those because we need to get them mature so we can harvest them. And the mature predator we can actually harvest. The same example as before it is actually, but again, this is a more complex design where we have prey, immature predator, and mature predator, and we need to have stability, we need to have survival, and we need to have a good income from this model. So again, as mathematicians, I believe this is a very hot topic of interest that you can go in and study potentially. This is again a combination of control theory and nonlinear analysis and potential chaotic analysis as well. Another case is tracking problems. Okay, for example, here we have a simple state space system, but let's say the output of the system needs to follow a reference RTA that may be, for example, nonlinear. So again, this leads to an algebraic equation. So again, we may want to consider tracking problems, which are class control problems, as differential algebraic equation problems. And of course, I'm sorry, in chemistry as well, I found a lot of examples of differential algebraic system. For example, I found an example of an isothermal batch reactor, but guys, they use extensive terminology on chemistry. I think that, it is there, you can study it, but I'm not going to include it because it's a bit too complex for us. But again, in chemistry, we will also find descriptor systems. Now, one application that I really want to discuss, because it is something that I study along with your own Professor Mahendra, and we have a lot of interesting, results here, is this. One approach to study descriptor systems is to use them in observer design and chaos-based secure communication. So what a lot of authors do, and we did it as well, is start with a simple chaotic system that we write it in this forum. If you see, this is actually similar to a state space system. The only difference is that we also have a nonlinear function. And what we do here is a very simple thing. We reformulate this system and take the transmitted input as a state. Okay, so let's say instead of the state X, we also have U as a state. So we have this augmented state, if you like. And this way, what we can do is take this simple state space system and write it in descriptor form, where we went from state of X to the state of XU. And why do we do that? Because think of this. Here as an input, we may have to design our own system, our own signal, I'm sorry, where it may be an information signal, for example, a sound signal or a text signal. So let's say that this input is potentially an information that we want to transmit. And this way we may transmit the information through the output, but we use a chaotic system, so the output here is pretty scrambled up. And if we design an observer for this system, we can actually estimate at the same time the original state, but also the input U. And if we do something like that, we can actually estimate the internal states of the system, which may be useful, but also this information signal. And we can actually manage to, transmit the input safely and potentially reconstruct it and estimate it and, reobtain the information that we transmitted. For example, here we did exactly that in a recent paper we have with Professor Mahendra. We took this hyper-chaotic Lorentz system and we used it as a signal S an information input that we wanted to transmit. And in this case, we consider a simple periodic signal, but we also did image transmission. So in this example here, we managed to create an observer for this whole system. And potentially what we did, if you will see in the next slide, we managed to estimate the states of the system, x1, x2, x3, and x4. We estimated them successfully. And also we managed to transmit an input, transmit it through a channel safely, because the information becomes scrambled up, as you see here from the outputs. And at the receiver end, we managed to reconstruct it. So again, you will see here this application where we actually, what we did, we artificially created a descriptor system based on our liking, because we wanted to reconstruct a transmitted input. And this, of course, can be very useful in communications. And maybe you can have some sort of industrial machine that you want to estimate some sort of unknown input. So apart from secure communications, which I do in my postdoc, and I also studied with Professor Makenda, you can potentially reconstruct unknown inputs for the system. So this is a very handy and cool design and application of descriptor systems. So this is the last part of our application. Let's see, has anyone asked any questions? Feedback link. Okay, we're going to discuss about your questions later. So let's begin. We still have time, and discuss a little bit about linear algebra tools. Because most of you, Professor Mahendra, we have time, right? We have 20 more minutes.
Yes, we have some time. We have around 20 minutes left.
Okay, cool. So guys, you are from the mathematics department. This is a workshop on linear algebra, on algebra in general. So you may want to ask me, okay, we went from state space to descriptor. So what algebra tools do we want? Do we need to have algebra? Do we need to have some sort of other tools to study descriptor systems? So yes, you need to have a lot of for state space systems and for descriptor systems as well. You need to have good knowledge on linear algebra in order to study their properties. This is the case for state space systems, but again for descriptor systems as well, especially linear ones, but I'm going to discuss non-linear as well. You need linear algebra tools. For example, in classic properties like controllability, which is actually the ability to steer a system from non-zero state to the zero state. So it actually studies whether we can drive a system to a desired behavior. In order to study it, Kalman has defined some classic rank criteria for state space systems. Similar rank criteria hold for descriptor systems as well. So yes, you need linear algebra. Again, for observability, which is actually the ability to estimate the internal states of the system, just taking a look by taking a look at the output. For state space and descriptor systems as well, you need to have knowledge on some matrix rank criteria. So again, you need linear algebra. Again, for an impulse-free system that I discussed before, if you want to study under what conditions a system becomes impulse-free, again, you can have, very simply, rank conditions and determinant conditions to specify that. And even more importantly, in state space systems, and I assume you definitely in your underground courses have some sort of course on matrix theory and system transformations. In state space systems, we generally apply very often some sort of transformation like Jordan canonical form. I'm sure you have heard the term Jordan form. And of course, controllable form, observable form. And, in state space systems, we do a lot of transformations, to decompose the system into subsystems. We can easily, observe system structure. We can apply faster control, like feedback design. So, transformations are very well known, and they are very common in state space systems because they're very helpful in studying systems and simplifying systems, This is the case as well for descriptor systems. So again, transformations, matrix transformations, which are a very big part of linear algebra, are also very useful in descriptor systems. And for example, let me give you a short example. One of the very classic transformations that we do in descriptor system is called the Weierstrass canonical form, or the Kronecker form, as some people say. And this allows us to take a descriptor system and decompose it into two subsystems. The first one is a state space system, which is very important. Okay, so we have two subsystems. The first one is state space. which we know, and they are unconstrained and very easy to study. And the second one is, if you allow me to call it the ill-conditioned system. So, you know, we have a descriptor system that is complex, and what we do actually, we decompose the simple part into one subsystem, and the complex part, if you like, you know, the ill-conditioned part into another subsystem. And, you know, this sort of behavior allows us to study the specific properties of the system separately, you know, study controllability and reachability and all observer design, feedback design, by studying each individual subsystem. And of course, since this is an equivalence transformation, you can go back and forth, you know. So every result you derive for this system also holds for the original system, because the transformation here is an equivalence transformation. See, for example, the solutions for this system, for the first system, we have a state space solution, while for the second subsystem, we have this sort of impulse solution. So you see that the bad behavior is moved on to the second subsystem. You know, this sort of you know, decomposition allows us to study them separately. But I want to finish off by saying this very important question, you know, because we saw some linear examples, and we also saw some nonlinear examples. So, you know, guys, being an algebra workshop, some of you may say, okay, for the linear systems, it's pretty understandable. We can use linear algebra tools. But what about nonlinear systems? You know, since we also have nonlinear terms, what happens here? Do we need matrix algebra? Is it, you know, useful or is it useless? This is the exact same question, guys, that I had when I moved on from linear to nonlinear systems. Because, you know, my PhD was on linear control, and I'm now studying nonlinear control systems. And my answer to that is, and I'm sure Professor Mahendra will agree as well, you absolutely need linear algebra tools to study nonlinear systems. Because you need to understand that for nonlinear systems, for example, observer design that we discussed before, and also controllability and feedback design, you may have to do some simplification to the system. So for that, you need solvability conditions. Usually these are algebraic conditions, and you need some sort of rank criteria to see if they hold. Again, even if the system is nonlinear, you may apply some sort of transformations. For example, Professor Mahendra as well has done so in many of his papers. Again, despite the fact that we have nonlinear system, we may be able to apply some linear transformations. And for example, for stability, for control, for observer design, as I showed you in our own paper, we consider some sort of linear matrix inequalities to make sure that the system indeed is stable, or that we can indeed do an observer design. And to simulate a linear matrix inequality, or to simplify it, again, you need linear algebra tools. So all of you, even if you go on to study nonlinear systems, whether they are mechanical, biological, economical, or whatever, don't think that linear algebra tools are not going to be useful. Indeed, they are going to be very useful for you, even if you go on to study nonlinear systems. So to finish off this presentation, guys, I want to thank you very much for being here. Descriptor systems, of course, apart from all those applications, we can have many issues like controllability, observability, point placement, stability. You can also study special cases which are positive systems. These are systems whose values can only take positive values because, for example, consider a population model. If the values represent population and people and cells, obviously they cannot take negative values. So these are called positive systems. You know, the negative values make no sense. We have delay systems. We can have problems related to optimal control, impulse elimination, equivalence transformations, you know, a lot of problems to discuss here. So we have a plethora of problems, you know, from chemistry, biology, engineering, mechanical systems, chaotic systems, secure communication systems, electrical systems. So a lot of problems to discuss here. So I want to finish off by saying I thank you very much all for your time, and the organizers and Professor Mahendra. And also I want to thank my good colleague here and friend and PhD student Ioannis A Kougioumtzoglou, because initially he helped me a lot with discussions about the emergence of descriptor systems in applications. So thank you very much.
Is there any question from audience? You can type your question in the message box or you can ask.
Okay.
Questions, please. Is there any doubt? Okay, there is no doubt. Let's thank to Dr. Lazaros. Thank you very much
guys,
for
thank you very much for
interesting
this.
talk. And I'm sorry that I did not inform your current affiliation and your current position to audience initially, because my team wrote the introduction, but I updated your introduction with your new CV. But actually, I forgot that line.
No problem. I think they took that
Thank you.
information from my LinkedIn, I think, or my
Thank you.
old CV. Don't worry. Yes, I'm a postdoc researcher of the physics department. No
Yes,
problem,
yes.
guys.
Okay, okay. Thank you. Thank you so much. Okay, so participants, we will meet tomorrow at 10:30 a.m. Thank you, everyone. Thank you, Lazo.
Thanks.
Bye-bye.
Bye.